Hey, let's go to the UK AI 2025 Alan Turing conference where all the best researchers in the field of AI in the UK meet. We're going there. I'm here with Michael. He's from the University of Bristol and he's gonna tell us more about their research, which is an amazing... what do you do actually?
Yeah, so we're at Bristol, we're working a lot on egocentric vision. So this is vision that you see from the first person. So you can see on the left here, we have a GoPro head-mounted, camera on head-mounted, and we're capturing the person's point of view and trying to work out what they're doing in the scene. So we've been doing that for about 7 or 8 years now at Bristol, and kind of working out the actions and the objects that they're interacting with, and so on.
Amazing. And then you do all the analysis with the help of the AI?
Yeah,
and you detect all the objects and you segment them?
Yeah, so we've got a lot of different data sets that we've released, going through a lot of different themes. So one of them is segmenting objects. We've done skill determination and expert knowledge. We've kind of expanded outside of just the kitchen into other areas as well. So all kind of aspects of daily living. So yeah, lots of different data sets that we've made openly available for research as well.
You have to do a close-up of those examples. Another question, and you can just do a close-up. Why is it important for the industry? Where do you see industrial applications of the research that you've done?
Yeah, so here we're presenting a stand going towards wearable assistive AI. So we could imagine a future in care homes where you might have a wearable assistant that helps you, making sure that your day-to-day is going well, you're eating the right stuff, nutritional information, not hurting yourself. But also beyond that, we could see, wearable technology becoming, the new smartwatch, right? So it's helping you in your day-to-day. Maybe it's teaching you how to cook new food, checking your health and other aspects, right? So these data sets allow industry to train these large models that can be used in kind of commercial products.
Amazing, Michael. So, can you do a prediction that in the future everybody's gonna wear AI glasses?
I think it depends. So we've talked to some people yesterday and they seemed really excited about wearing these things, and others, maybe they don't want to know what nutritional information is going into their food, right? They just want to put more butter in and not worry about the fat content. So yeah, maybe, I don't know. It's hard to say at the moment.
And have you already done any industrial applications with your research, or is that a work in progress?
So it's currently a work in progress. We've had people reach out to us. So we've had people from commercial kitchens, so chefs, ask about kind of training models for AI, but nothing. Maybe some stuff in the pipeline, but nothing kind of concrete yet.
Amazing.
Okay.
All the best. Thank you. There. We're here together with Tony from the University of Nottingham, and he will tell us more about his amazing research in chemistry. Tony, hello.
Hi, nice to meet you. So I am part of the AI for Green team, and we work from the University of Nottingham, and we are sponsored by the Royal Academy of Engineering. And what our main research goal is to provide sustainable and environmentally driven chemistry. There's a big problem in chemistry with it's very impactful on the environment. So our main goal is to mitigate the damage that causes by providing AI tools which can, help suggest more green and sustainable choices to those who want to do their chemistry.
Amazing. Yesterday, Tony already showed me their product, which is a software which can do an amazing thing. We will show it later. But first, where do you see any future industrial applications of your research and of your findings?
That's a good question. So our research is obviously very much on the forefront of drug discovery. There is this current quite a big gap between the big pharmaceutical companies and what the average person who wants to, create a molecule, create a drug, what they can actually access. And a big aim of ours is to make everything open source, to make it accessible to the general public. So I think one of our key industrial applications is not necessarily the big pharmaceutical companies, but the littler guy who can access our work completely open source, and they can use it however they will, and we've got a lot of different tools which will make them trying to provide new drugs, provide different ways to create new molecules, and using different solvents, and there are loads of different features on our app which will help smaller companies and schools, for example, to create molecules in the way that they would like.
Amazing. So in a way we could say this is a democratization of science.
Yes, massive.
Or to make science or tools for the discovery of new molecules and so on more accessible. Later we will show how the product looks like, but now an additional question. we are on the AI conference, and AI is an integral part of your software, of your product. So, can you describe me in which steps did you use AI?
So there are two key facets, particularly in my work, where AI is kind of related. So I work on this thing called retrosynthesis, which is the process of kind of reverse engineering a molecule such that you can find new ways to create that molecule. And in that process, the very first step is for us to create this neural network which basically tells the computer how every molecule can disconnect, because a computer can't just look at a molecule and decide, oh, we're going to split it there, there, and there. We need to kind of train that so that it can understand where the connections need to come from. So we use a deep highway network which has lots and lots of hidden layers, and we train that on 12 million compounds from the US Patent Office, and that is the first kind of AI step in our process. And then that's followed up by, that will create this kind of search tree of structures or of molecules. And as that search tree gets larger and larger and larger, we need efficient search algorithms to look through those. And that's the second step. We use the Monte Carlo tree search to efficiently search through our very large search space to find the best route to create a molecule.
So to simplify, amazing answer. To simplify it is, if I understood it correctly, is, you know, you got those big molecules and you have to find a way how to break them down into smaller pieces. And this program helps you with that process. And the program also tells you how to then combine those pieces back into the big molecules.
Yes.
Because the big labs, the big pharmaceutical companies, they do produce those big molecules, but for the everyday people or for the everyday researchers, this is a mystery how those big molecules are created.
Yep.
And that's where your software solution or your team's solution comes in place.
Yep.
Okay, thank you. And now we will look at the application.
This is our main app. You can visit this app if you go to the aiforgreen.homepage at the top, and the retrosynthesis is my main area of work. What one can do is they can input a molecule here, and then they can choose a various number of search enhancements, whichever they choose, and then you can choose which kind of search configurations you would like, and then all you have to do is click New Retrosynthesis, and then after a little bit of time, we will provide several routes in order to make that compound. So this is the example compound we used, and as you can see, we now have several routes to make that molecule.
Amazing. Thank you. There, I'm together with Maria. She's a doctor from the Aston University from Birmingham in the UK, and she's the lead research of this product, of this project, that tries to solve the problems of the, she will tell us more.
So what we're trying to do here is control a junction in real time based on live CCTV footage. Mm-hmm. The way that we do that is that we feed the images to an AI agent that works with deep reinforcement learning, and we ask of it to learn with time to control the junction, control the traffic lights in an optimal way. So the way that we do that is quite clever in that we don't tell it which features to look at. Rather, we let it learn which are the important features that lead to the optimal behavior. All we're giving it is the pictures and the reward on its actions. The actions are the traffic stages that are allowed, so the combinations of red and green in the lights that are safe. So it chooses that at those in the beginning, not very effectively, but we give it rewards telling it whether it did well or it did not so well. The sort of rewards that we give it take up information from the traffic throughput, so how many cars or how many pedestrians pass through the junction at any given time, the waiting time, the delay, the travel time. And so we form a combination of that, and that's the reward or punishment of the agent. So it learns from that. Now, how does that compare with the state of the art? So there's two main types of traffic junctions. One is the time traffic junction, so it's 3 minutes this way, 3 minutes the other way. Yeah, hard-coded, not very good. The majority of the junctions, especially the busy ones, will have some loop inductors, magnets buried under the road that are effectively metal detectors and count cars. So the optimization there is again hard-coded, but it's adaptive in the sense that it prioritizes the busiest sides of the road.
But your solution is fully dynamic.
Our solution is fully dynamic. It tracks traffic in real time and responds to the traffic in real time. So our solution is not only based in number of cars, it's based on the features that the AI has learned. So it could be number of cars, it could be type of cars, it could be the deceleration as they arrive into the junction, it could be the space between the vehicles. There's lots of that. When we compare like with like, so when we compare our system with the existing system, the existing adaptive system, ours does much better in terms of waiting time, in terms of travel time. It does very well, better than the existing one in throughput and so on. The cost is also remarkable. So ours, with the most expensive cameras, the fanciest we could get, costs around 5K UK pounds. Whereas the existing one for a four-way junction would cost upwards of £40,000. The other thing, beyond comparing like with like, because ours works with cameras, it can do so much more. So, for example, we can teach it based on the reward functions that we give it to prioritize emergency vehicles or public transport vehicles. Or maybe near a school, you want it to prioritize pedestrians and cycles. Near a work site, you want to prioritize trucks. And you can do that tailored for each junction that you're controlling. Yeah. We're now deploying this at the junction near the hospital in Coventry.
Okay.
And we're looking forward to harvesting the results from that. The next step is deploying in other nearby junctions in order to do network control, multiple locations
among the same road,
which will mean changing the reward functions to look at not only local but also global performance. And the next step after that is to use AI to discover which are the junctions that are worthwhile controlling. You don't need to control everything. There are some key ones, and transport engineers will know which ones they are, but we are always surprised when we let the AI discover which are the key ones. Sometimes there's variation, and that's interesting.
And the interesting aspect, among many others, is that you use real-time data.
Yes.
For each particular junction, you use its own camera capturing data, and then you build your model on top of it and the solutions.
Absolutely, and that's important because even within the same location, we have variation of behavior at different times of day. The commuter time is different. The 3 o'clock morning time where people might go clubbing could be totally different. Sunday when there's a football match, it would be totally different. Different traffic actors, different traffic behavior, and it's important to be able to control the traffic optimally for what you have, the situation you have at hand.
Excellent. Can we now look at the slides? And would you mind just to go directly to the screen? And we can simultaneously describe just in maybe 2 or 3 sentences what do we see on the screen.
So this is the location where we are deploying. Oh, bear with me.
Hey, maybe you can go here. It will be. Thank you so much.
So this is the location in Coventry where we're deploying. You'll see on the top left-hand side the view we are getting from our 360 fisheye camera, and then we unwarp that. And you're seeing below that the 4 images of the 4 approaches as the cars come into the junction. The counts that we see there, we don't use in the AI. We're using them for the validation. So we don't explicitly count cars in our AI, but we are counting them for the validation to see how well our agent is doing. So the decision-making model that you see to the right of these 4 pictures is the AI that we've been talking about, that looks at the pictures and decides the configuration of the lights among the allowable safe configurations that the city council gives us. For example, the transport engineers have given us. So the AI takes as input the fisheye view that you see in the top left and returns as output the configuration of the traffic lights. One thing that is quite interesting to see, because that's the AI, but you see our AI learns by trial and error. This is our convolutional neural network, the input and the output, and then how it's organized. But as we said before, this agent learns by trial and error, and it's driven, the learning is driven by the rewards. Now, nobody's going to let you lose on their junction and wait for your agent to learn. It takes a bit of time. So what we've been doing is we've been building simulation to allow us to do the training. Now, Sumo is among the state of the art, so that's on the left, the green bit. It's a 2D simulation, which is very good, very useful, but it always assumes that everybody plays by the rules, they follow the speed limits, they don't get into the wrong lane, they always stop at the stop line, and so on. Not many people drive like that. Now, if you want to train your agent in a more realistic scenario, you might want to extract information from the real world. We started by doing traffic 3D. So this is our simulation. It's our simulation in a 3D environment. That's useful because it gives our agents images that look like what they might see in real world. So we can change the weather, we can change the traffic actor behavior there. But we also wanted to inject more realism. My background is in simulation, and I'm keen to be creating simulations that are accurate. So what you see here at the bottom, so this is a junction in Russia. And on the left-hand side is the real junction as you see it on CCTV. What you see on the right-hand side is us having extracted the information from that junction using a graph neural network, built a simulation which we then render in CCTV, and this is the ideal scenario in which we, in which the ideal framework in which we train our agents. So there, the agents behave in the way that the junction behaves in that particular time. And what we can do then is go and manipulate it and synthesize further data that I might have days and days, months of CCTV footage, but not have handy. So a particular type of weather phenomenon, particular type of traffic accident. I might want to make all the cars red if I feel like it. So we can manipulate that. And that's a very good, we found, simulation for that.
I think it was an amazing presentation and an amazing solution. Let's stop at this point.
Thank you.
If you agree. And Maria, thank you for your time.
Thank you.
And the best location for the conference. Look.
On precursors of sexual behaviours. So it was a project that was focused on violence against women and girls.
You know collaborative robotics?
No.
Ashima. She's a CEO of the Datambit, which is a deepfake detection for audio, video, and images. Can you tell us more about your service?
Hi, it's lovely to meet you, and very interesting place here, Alan Turing, hosting the AI UK. Brilliant people, very knowledgeable, and we're really happy to be here. So what we do is we do deepfake detection. We do the detection on audio, video, and image. And we've been tested by the UK Home Office. We've been part of the challenge, AI Innovation Challenge Global for City of London Cooperation. We've been spotlighted by the FCA. So we've really built out the pillars of trust and performance. As I said, performance is audio, precision of 0.99 and video of 0.96. So what we do is essentially protect people from crime, cybercrime, the use of generative AI when it's used maliciously, when it's used for purposes that are not conducive to the company or the individual.
So they are able to detect 96% of fake videos and 99% of fake audios. Where are your industry applications for your product?
So we're a startup, and we are building the verticals. But right now, our detection could work for identity for banks for onboarding, for recipient accounts where they're mule accounts, where people are receiving money to check whether they're real people. In government, in elections, for example, in insurance for claims. I mean, the list goes on. But we're in the process of onboarding with the Home Office. So we hope to do a lot with the UK government because this is where we are based. We're based in London. And we also hope to do a lot with banking because of the cybercrime and fraud that's happening.
Excellent. Would your product be possible without the AI? What technology do you use in your product? At least the things that you can reveal.
Okay. Absolutely not, because our product is based on the fact that you can use generators to generate deepfakes, which are AI. It's AI generation. It's generated using AI, which is what the generators use. So we counter it by building our own proprietary detectors and detection systems, which essentially counter what's happening and detect it. Therefore, we build our models on the basis of neural networks, deep learning and neural networks, for example. So yes, we are very much in the AI space. And AI we build for detection, therefore we build with AI.
Anything else that you want to share?
That's it.
Okay,
Great.
thank you, Shima.
Lovely to meet you.
Represents the quickest route to navigate through. The pink route is the most fuel efficient. The most fuel efficient takes 2 hours longer, but it will save the same.
I'm here with Esther. She's from the Incubator for AI. This is a UK governmental agency, and she will tell us more about their mission and what do they do.
Yes, so the Incubator for AI was set up a year ago by the UK government to try and bring tech expertise into government to solve some of the biggest problems we have right now, whether that's to do with healthcare or to do with more general problems of productivity in the UK.
Okay.
So we've got some projects.
Can I just comment on it? It's amazing because you see, UK government is trying to save some money and to speed up the processes to become more efficient and so on. And so they established their own incubator for AI projects for the civil servants. And now we're going to see some projects.
Absolutely. So we have a few projects right now. Some of these are to do with the productivity that you just mentioned. So Redbox is one where civil servants can summarize documents and also kind of chat with frontier LLMs in a safe, contained way. Consult is one where we're doing thematic analysis using LLMs of survey results that are coming in from citizens. Parlex and Lex is more kind of where we've explored the abilities of semantic search. So seeing how we can try and use all this data we have in government.
Let's go to the first one.
Okay. So Redbox. This was one of our first products that we came out with, and it's the one being used by the most people in the civil service right now, about 5,000.
What's the use case?
Basically, you have loads of documents, you want to put them into Redbox, you upload them, and then you can chat with your own documents. So you can ask, what was the deadline I was meant to meet?
You receive 10 emails.
Yep. Download them, put them in.
Helps you to chat with the substance of those emails.
Absolutely, or summarize it as well.
Is it useful? Is it used?
It's very much used. We've got 5,000 users at the moment, so they seem to be enjoying it.
Thank you.
Thanks.
Bye-bye. Amazing, yeah.
Government's changing a policy on something, they need to
Consult
with the public, which often means a survey with lots of responses, and what we've built is an AI package.
So to educate and consult the civil servants about the new legislation.
No, it's about the process of the government consulting with the public to understand their opinions.
Amazing.
And then when all those responses come in, finding the themes within those responses.
With the Nathan from the Alan Turing Institute, and he also collaborates on the project which is they try to predict the weather. And Nathan will tell us more about it. He's a researcher. He has a PhD in particle physics, if I'm not mistaken.
Right, yeah.
He's an amazing guy. He's going to tell us all about the weather predictions, and also the first question, why is it easier with the AI to predict the weather than it was with the legacy old school models?
Yeah, great. Yeah, lovely to meet you. It's great to be here in AI UK. What we've been doing, so the project here is global weather prediction. So we have a big graph neural network model that's taking in weather at some point in time, and we're predicting it out to 6 hours, 12 hours, 3 days, 5 days, that sort of thing. You talked about, I guess, sort of legacy models. So we're still using these physics-based models, but the AI models are much faster to run. They can take minutes on GPUs, whereas the other models can take many hours to run on very big CPU farms. So yeah, that's why they're great.
Nathan, can you explain to me, because I'm not in your industry, not in your sector, so it might be a dumb question, but still, how are the old models for the weather prediction operating versus the new AI-driven models? Can you explain it in a very concrete way?
Yeah, of course. So the models we have now, a lot of them are still in the very early stages. So the model that's going to appear behind us at some point, it's not operational. But sort of how the old models work, it's exactly the same actually. So the weather prediction comes in. We look at the weather, data about temperature and the rainfall and humidity and things like this. That goes in, and then the model does its thinking, and then the prediction comes out, and that's the weather 6 hours later. And that's exactly the same as the AI models, but the AI models are running on GPUs, really new hardware. And that's sort of part of what's made this AI revolution so great for weather, is that the models are being trained to work really well, and they're running much faster.
So what's the differences in time and in the processing power needed to run such models, old and new way?
Yeah, that's a great question. So it's actually much less compute. So these models take a lot of compute to train, just like OpenAI, any of these large companies. There's this upfront cost of loads of GPUs, spreading the model and the data across all of this compute. But actually, when you're running it, you can run these models on a single GPU, like a consumer card you could buy in the store. To run a legacy weather model, you'd need a CPU farm of tens of thousands of cores, totally inaccessible to the general public or even small companies. But weather models like this, this is making it possible to really democratize access to this kind of tech.
So in a way, you can run those models on a single GPU, whereas the old models for the old physics predictions, for the modeling, you needed a whole cluster of computers, like the whole data center,
Yeah, that's right.
Let me ask you another question. You trained your model on the UK data. How easy would it be, or how difficult would it be to use it for Slovenia's weather prediction? Slovenia is a country between Austria, Italy, and so on.
Yeah, that's right. So great question. So the model we built does global weather prediction, so for the entire world, but it's true that we're going to specialize it over the UK. What people could do, for example, are, there are open models, including ours, that exist. If you have, if the Weather Institute of Slovenia has better data for Slovenia than other places in the world, you could take a machine learning model and fine-tune it for the region that you care about, because that's exactly what we're going to do, here with the UK Met Office. We're going to be fine-tuning over that small area using special data that we have access to.
And one last question.
Yeah.
Where do you see the future of AI in your industry of weather prediction? Where is it going to go?
So this is a really cool question because in the last 5 years, they say there's been like a quiet revolution in AI for weather forecasting. Before 5 years ago, AI models couldn't even come close. Now, the best AI models are starting to beat state-of-the-art best physics-based models, and they're only getting better. So I'd say like the future is within about 2 to 3 years. I think all of the major weather companies and meteorological offices will have AI-based weather forecasts, which will be really exciting, and we'll have better predictions for like extreme weather events, better uncertainty quantification. Yeah, it just feels like a very exciting time to be in this field. Yeah.
Thank you, Nathan. Thank you for this excellent conversation.
Yeah, that was a pleasure.